Alright, so far we focused on iterative algorithms. So now let us do the recursive algorithms. We saw recursion in 228 and should have seen this in the earlier classes too. So we can say recursion or a recursive function, to start from there, is a function that calls itself, right? That's what recursion means. Now let me again, I should have said this in the data structures course, but let us also do that now. So one classical example we can use to understand recursion is the factorial problem. So the factorial problem is, we know n factorial can be written as n minus 1 factorial times n. Okay, so for example, if I want to compute 5 factorial, and how we get this, so let me explain that here. 5 factorial, for example, is nothing but 1 times 2 times 3 times 4 times 5. So this 1 times 2 times 3 up to 4 can itself be considered as 4 factorial times 5. So in general, I can say n factorial is n minus 1 factorial times n. So that's how we get this. So that means if I want to compute 5 factorial, I can compute 4 factorial, and whatever the result of 4 factorial is, I can multiply that with 5 to get 5 factorial. So I can say f of 5 is f of 4 times 5. Now I don't need to know answer for f of 4 right away. I can use this recursion again. So let me write it in general. So f of n is f of n minus 1 times n, and this is true for n, and we'll fix that quite soon. But let us continue this. So f of 4 by using this recursion can be defined as f of 3 times 4. Okay, so f of n is f of n minus 1 times n. So f of 3, again we don't need to know answer right away, is computed like this. And f of 2 is f of n minus 1, so 1 times 2. Now what about f of 1? F of 1 is f of 0 times 1. Now you may think, how can we, when can we stop? We cannot say something like this, because the factorial is defined only for integers greater than or equal to 0. It's not defined for negative integers. So f of 0 is like what is called the terminating condition or the basic condition, and f of 0 need to be specified. So f of 0 is 1, 0 factorial is 1. So that's a well known thing, everyone knows it, so it's not something that you have to find out. So we can say 0 factorial is 1. So once you know 0 factorial of 0 is 1, we can substitute for that here. 1 times 1 is 1. So that is f of 1. Then f of 2 is 1 times 2 is 2. And using this you can find f of 3. F of 3 is f of 2 is 2 times 3, which is 6. So now f of 3 is 6 times 4 is 24. F of 4 is 24 times 5 is 120. So this is how you compute a factorial of 5. Now this is done in a recursive fashion, in the sense that to compute factorial of n, you compute first factorial of n minus 1. Now how the execution will be done is, I did not show it here, but let me use my other slide. So to compute a factorial of 5, you need to compute factorial of 4 times 5. But you don't know the answer for factorial 4 right away, so you put that in a memory stack and call the factorial function again. So factorial of 4 is factorial of 3 times 4. And you don't know the answer right away, so keep it again on the stack. And keep piling the stack until you reach factorial of 0, which is 1. So stack is last in first out fashion. So you clear this, what's called stack frame. Each particular unit is called a stack frame. The control goes to this stack frame. Using factorial of 0, you compute factorial of 1, which is 1. Then using this stack frame, compute factorial of 2, which is 2 times 1, which is 2. Now using this, you compute factorial of 3, which is 3 times 2, which is 6, and so on. Now as you use this stack frame, you clear them off from memory. So at the end, on the top of the stack will be factorial of 5. Okay, so as you use them, you clear them up. So this is not a very straightforward approach, in the sense that you have to use a lot of memory to keep building up the stack frame. So that's why it becomes a problem if you really want to build a larger stack like this. You will probably go out of memory. So that's why you will not go through recursion unless that is the only approach you can use to solve the problem. So you should try your best to do iterative approach. So only if you cannot solve using an iterative approach, you go through recursion. So it is on practical basis, it's more time consuming as well as space consuming. So let's do the theoretical analysis for recursion. And so the time complexity you will get for this factorial problem is going to be the same as what you get both the iterative approach as well as recursive approach. But given a chance, you should implement an algorithm with an iterative approach compared to the recursive approach. Okay, right. So let us work it out here. Any questions so far on how to compute factorial? Alright, so in terms of the basic operation, okay, let me show the pseudo code, which is going to be quite simple. So the pseudo code for the factorial problem is very simple like this. So if you want to compute factorial of n, where n is the integer input, you check if n is 0. If n is 0, return 1, because 0 factorial is 1. Else, return factorial of n minus 1 times n. So that's all the pseudo code is, and even the original actual code is going to be as simple as this. So if you look at the basic operation, and I hope everyone is clear by now what you mean by return f of n minus 1 times n. So if you want to compute, say for example, f of 5, it is f of 4 times 4. So you need to, the function calls itself, that's where recursion is. So you need to compute what is f of 4. And for that, since you're calling n with n equals 4 now, it will check n equals 0 or not. Else return f of 3 times 4 and keep going. So the basic operation here is the multiplication operation, where you do f of n is f of n minus 1 times n. That's done repeatedly as you do this recursion. So what we can do is analyze how many times you are doing this multiplication. So I am introducing a notation called m of n, is the number of multiplications to compute f of n. So the number of multiplications done to compute f of n is denoted as m of n. So f of n we know can be written as f of n minus 1 times n. Okay, so that means whatever be the number of multiplications to compute f of n minus 1 plus one more multiplication will get me the number of multiplications needed to compute f of n. Okay, so I can introduce, so this is called recurrence relation. Now even here you keep going until f of 0, you get f of 1 is f of 0 times 1, and f of 0 is 1. It's not, we cannot solve f of 0 using this recurrence. So we can say this recurrence relation is true for n greater than 0. If n equal to 0, f of 0 is 1. Okay, so this recurrence relation is true. So it's called recurrence relation. Is true for n greater than 0. Then f of 0 is 1. So let us use a similar approach to get a recurrence relation for m of n. So the number of multiplications to compute f of n is m of n. That means the number of multiplications to compute f of n minus 1 can be denoted as m of n minus 1. That's the number of multiplications to compute f of n minus 1. Plus one more multiplication. So this is that one more multiplication. Will get us f of n. So the number of multiplications can be represented using this recurrence relation for n greater than 0. And if n equal to 0, we really don't need to do any multiplication because we know the answer right away. Factorial of 0 is 1. So this is the recurrence relation for m of n. So this m of 0 equal to 0, conditions like that are called the basic or terminating condition. So how to solve this recurrence relation like this? So in your discrete structures class, you should have seen an approach of induction. And so we're not going to go through as theoretical, as detailed as the other in discrete structures. We are going to do it more in a very simplified high level approach. So given this m of n equals n minus 1 plus 1 for n greater than 0. So what I can do is I can say m of n minus 1. So replace n with n minus 1 in this recurrence here. So if I replace n with n minus 1, m of n minus 1 on the right hand side is going to become m of n minus 2 plus 1. Now what I am going to do is I am going to substitute for m of n minus 1 this m of n minus 2 plus 1 in this equation here. And so I am going to substitute for m of n minus 1 m of n minus 2 plus 1. So that will make my m of n to be m of n minus 2 plus 1. So the entire term just comes from m of n minus 1, and there is a plus 1 inside. So that's going to be m of n minus 2 plus 2. Now I can write this m of n minus 2 similar to this as m of n minus 3 plus 2. So now I can substitute for m of n minus 2 here as m of n minus 3 plus 2. So all I am getting is m of n plus m of n as m of n minus 2, which is m of n minus 3 plus 2. might have made a mistake somewhere. 1 second. M of n equals M of n minus 1 plus 1. Sorry, M of n. So all I'm doing is substitute n instead of n minus 2. So if I substitute n equals n minus 2, this is n minus 2 minus 1, which is M of n minus 3 plus just 1, not plus 2. I'm sorry for that. So I'm going to substitute for M of n minus 2, M of n minus 3 plus 1, which is M of n minus so M of n is M of n minus 2 plus 2, so that is M of n minus 3 plus 1 plus 2, so that is simply M of n minus 3 plus 3. So let me go over it one more time. So the number of multiplications to compute n factorial is the number of multiplications to compute n minus 1 factorial plus this one more multiplication. So that's how you get the recurrence relationship. And this is true for n greater than 0. And for 0 factorial, you don't need to do any multiplication. So the number of multiplications to compute 0 factorial is simply 0. So this is called the basic or terminating condition, and this is the actual recurrence relation that you have to solve. Now we solve this by the induction approach simply by reducing it to lower order terms. So instead of n, I am going to replace it with n minus 1. So instead of n, I have n minus 1. So here, instead of n minus 1, so that's going to be n minus 1 minus 1, that is M of n minus 2 plus this 1. Then I'm going to replace M of n minus 1 with M of n minus 2 plus 1 in this recurrence relationship. So I'll get then M of n equals M of n minus 2 plus 1 plus this 1, so that is M of n minus 2 plus 2. Now I need to know what is M of n minus 2, so I can go back to the original recurrence and substitute instead of n minus 2. So this is M of n minus 2, replace n with n minus 2, that is n minus 2 minus 1. So it is M of n minus 3 plus 1. So now I can substitute for M of n minus 2 to be M of n minus 3 plus 1. Then that's what I've written here, M of n minus 3 plus 1, then plus this 2 comes here. So that is M of n minus 3 plus 3. So it can keep going like this. That's the induction part. I can say in general M of n. So you should see a trend now. If it is M of n minus 1 plus 1, or it is M of n minus 2 plus 2, or M of n minus 3 plus 3. So 3, 3, 2, n minus 2, 2, n minus 1, 1. So in general it is M of some n minus I plus I. And that's again for n greater than 0, all this stuff. So that's the more general format. So we need to again still solve for M of n using this M of n minus I plus I. Now look at the basic condition. The basic condition is defined for the parameter for the m to be 0. M of 0 is 0. So if you can reduce this recurrence all the way to something like M of 0, means we have an answer. So how to reduce this recurrence all the way to 0? We can substitute n minus I, the term inside this thing. If it is equal to 0, then we know an answer for M of 0. So that's what we'll do. We'll substitute n minus I equals 0 and find what value of I we can solve the recurrence. So if you say n minus I equals 0, we can say I equals n. So substitute I equals n in this general recurrence. We're going to have M of n equals M of n minus I is 0 plus n. Instead of I, now substitute n. So M of 0 is given as 0. So it is 0 plus n, which is n, and that is theta of n. So the number of multiplications needed to compute n factorial is theta of n. Now this is the same thing we are going to get with the iterative approach too. The iterative approach, I can, if you wrote it in 118 or 119, I can declare my factorial temporary variable to be 1 and run a for loop from I equals 1 to I less than equal to n, I plus plus, and set factorial equals factorial times I. And this could be the program you should have written in 118 to find factorial. Okay, so here you see it goes from 1 to n. So factorial is 1 to begin with, then if I is 1, it is 1 times 1 is again 1, then I equals 2, 1 times 2 is 2, that's a new value for factorial, then I equals 3, 2 times 3 is 6, and so on. Okay, so and I equals 1, factorial will be 1 times 1, which is 2, I equals 2 is going to be so 1 times 1 is 1, 1 times 2 is 2, then I equals 3, factorial is 2 times 3 is 6, I equals 4, factorial is 6 times 4 is 24, and so on. Then I equals 5, factorial is going to be 120. So if you look at the time complexity, this is solved using the sigma notation. I equals 1 to n. The basic operation is multiplication operation inside the for loop, and you do the multiplication once for each value of I. So you have 1 inside the summation. So this is sigma I equals 1 to n 1, and this is again upper limit minus lower limit formula, n minus 1 plus 1, that is simply n. So this is also theta of n. So theoretically, both the recursive approach as well as the iterative approach gives us a theta of n time complexity for the number of times we do the multiplication. But I explained earlier that the recursive approach will take more time to do all this stack management. So a function calls itself by passing the parameters, so you have to substitute back and then solve. Whereas the iterative approach doesn't go through anything like that. We just have a simple for loop and do a multiplication for each iteration of the for loop. Okay, and there's only one temporary variable, the factorial variable, that needs to be stored and computed. So if you run both the recursive and iterative version of factorial, you will see that the recursive approach is, on practical basis, is more time consuming. Okay, any question on this? Okay, so please go through all this stuff after the class. It'll be easy to understand right away.